Hello, everyone, and thank you all for joining us. The views, opinions, and technical analysis presented during this webinar are those of Stepan Company. They're not necessarily those of UL. The appearance of this content on UL sites does not constitute endorsement by UL or its affiliates. Today's webinar is Speed to Prototype, high throughput, high throughput for sulfate-free shampoos and cleansers. And is presented by Stepan. Your presenters today are Cyril Bhattacharya, Senior Research Chemist, Renata Batikas, Global Marketing Manager, and Greg Dado, Technical Director in the Formulation Technology Research Group. My name is Derek Betcher with UL, and I'll be moderating today's webinar. Please type your questions in the question box located on your screen. We're recording today's event, and we'll send you a link by email when it's been posted to ulprospector.com. Now I'd like to hand it over to Renata. Are you ready to begin?
Yes. Thank you so much, Derek. Welcome, everybody. We're very excited to have you today as we talk about high throughput for sulfate-free shampoos and cleansers. For today's agenda, we're going to break this down into 4 sections. We're going to start with the problem. We know sulfate-free creates more complex systems, and that requires a lot more data. The solution to that in our second section, presented by Greg, will be about that high throughput system, but in combination with guided experimentation. And then we're going to take that solution and apply it. Cyril is going to provide a real-life sulfate-free formulation example of how we will tackle that challenge in a more efficient way. And then finally, we'll go through the partnership. Stepan turns that data into the decisions that make your formulating challenges much more efficient. So let's get started. Always start with the problem. We know that these systems are complex. Like we said, much more data is required. Sulfate-free isn't new, but it really has become table stakes. We're formulating with them much more often than we did just 5 years ago. And what we can see from this data from Intel is that what was once a point of differentiation is really now expected. Sulfate-free is the number 2 most commonly used on the front of the bottle free from claim. There are many different types of claims that have categories. These are those free from. What ingredients, what positioning are we looking to remove? It doesn't matter what region you're in. This is global data. Every single one, sulfate free, is number 2 and is about 39%, just shy of 40 of all launches. The first one is paraben. That's been around for a while. Not surprised there. We want to make sure that ingredient isn't in these formulations. But it's ahead of things like mineral oil, fragrance, silicones, even oils and palm oils. So it absolutely becomes something that we all need to formulate in our day-to-day. As we said, these systems are far more complex than the tried and true sulfate-based systems. Those systems have 10 to 15 distinct INCI names, depending on how much you're adding to that claim language. There's a vast amount of water, and that primary surfactant is typically 1, sodium lauryl sulfate, maybe sodium laureth sulfate, or a combination, but it's pretty simple. You add your tried and true secondary surfactant of cocamidopropylbutane, and to thicken this system, which is really important to the experience of these formulations, you can add salt. These things thicken themselves with the presence of salt, so it makes it really easy. Now that we've switched to a modern sulfate-free systems, these are so much more complex. There's 15 to 30 plus distinct INCI names that are used in these formulations. You might start with an actual secondary surfactant. Cocamidopropylbutane is used often, and it's usually second after water instead of that primary surfactant. And then instead of a single one, you've got all types of coprimaries. Maybe there's multiple with an alpha olefin sulfonate or an alkyl polyglucoside. Then you're adding a different primary surfactant as a coprimary, whether it's amino acid based or maybe a sulfosuccinate. And not only do you get one secondary, you might add a second one because building that viscosity is so difficult. So maybe it's acetylbutane or a sultane. And then to thicken it, you might get away with sodium chloride. That's much more challenging than the sulfate-based systems, but maybe we need a gum or a guar or a different type of polymeric thickener because they're so challenged to get to that performance. Which leads to, how do we get to that performance? They're completely different as well. In a sulfate-based system, I can add my primary and secondary 2-component system, add my salt. It's going to build viscosity really close, maybe even without salt, or just a little bit. Whereas a modern sulfate-free system, that salt curve is shifted to the right. You need much more salt, and it's not going to build as high a viscosity as we require for these cleansers and shampoos. Second, clarity and stability, much easier with sulfate-based systems. We can get something nice and clear. It's easy to solubilize, whereas the sulfate-free systems tend to be cloudy or translucent. We need a bit more solubilization to make sure that those get to the appearance that we're looking for. And then it's not just about viscosity and clarity, foam. I can build foam with sodium lauryl sulfate and sodium lauryl sulfate, super easy, big bubbles, because there's not much else taking away from it than what we see in modern sulfate-free systems. It's much less because the amount of additional ingredients we need to add and the different combinations that we have to put together diminishes that foam, which is super critical to consumers and the aesthetics that we need in these cleansers and shampoos. So, with all of that complexity and challenge of getting to a performance, that all drives time and tedious repetition. I know we've all seen it as formulators or when we're trying to get to that specific product that we need to produce. We can start in this process with expertise. It's an excellent starting point and really critical. We get a lot of information on where that starting point is from that initial understanding. But these systems are really hard to predict. Maybe we get lucky, or we know that we've got this is that one chassis that I can always depend on. But we need to be able to be more unique, differentiate. So, to build upon that, we might use traditional methods like salt curves, everyone's favorite methodology for building viscosity. They help tune, but it's limited to single response insight. We have to run every sample at every salt level to better understand viscosity. So, another element that we've been able to introduce over the past few years, and a lot of people will use, is design of experiment, or DOE, if you're familiar with it. It improves structure. It is a software based system that helps us map, but it requires a lot of data, sometimes too much data, which can take a lot of time. And those high dimensional spaces, right, exactly are slow to map. We might not be willing to produce every single one of those samples to get to the answer that we might be able to do via guess and check. So you get this result that is repeated bench iteration that we've all had to deal with, and it becomes much more challenging to get to what we need when it comes to formulation. What we want to do, and as technology advances and our understanding improves, is to shift from that trial and error to data driven formulation. We all are aware, don't need to remind about AI in the workplace. It really is reshaping how we get our work done. Over 64% of companies already are using machine learning in some capacity. It's well understood that faster decision making, it's an automation of tasks. We can get to data driven workflows. Maybe that's in language based systems like ChatGPT or Copilot. So these are the areas that are rapidly growing. But it's not in just the way that we do work, it happens in formulation today as well. We see a 23% annual growth rate of AI in the cosmetic formulation market. This could be areas like deformulation, ingredient databases, or consumer and trend analytics. It already is increasing what we see in the chemical industry. What we want to do, take a second and poll the audience. Get your participation here and take a pause. We want to know how many of you are using formulation AI in your day to day. Derek, could you pull up the poll for me? Perfect. So like I said, you've got a few options here. In formulation work, not your Copilot, not your ChatGPT, which of those specific formulation databases are you using today? None at all? Still at the bench? Are you aware of it? Experimentally, maybe using it? Is it for select projects or, hey, it's part of your everyday workflow? Submit your vote. Give it a few minutes. And almost half of you are experimenting with it occasionally. So starting to learn what that looks like, but not every day. Thanks so much for participating. That's great. So we know that it's a part of the formulation space. But how do we convince ourselves that this is the best way to guide our experimentation, not a replacement? We know that it can't be fully automated. Today, maybe the pieces that you're using, that you're experimenting with, it really is about that support tool. I'm going to learn about the ingredients. Maybe it can give me a starting place, but it's not a replacement. We have to use interpretation, also check. It depends on some of those trade offs. What do we see as usable? What do we not? And it involves sensory and performance nuance. Maybe it's able to find me the ingredient that I need to use, but when it comes to actual interactions between those systems, it's still not advanced enough. So, what we see is the need to combine all that decades of formulation expertise with a much more structured way to generate reliable data. We need more of that data more efficiently to make those decisions much more easier. Now we've talked about the problem and we see how we can provide a combination of those. I'm going to hand it off to Greg to talk about the solution.
Thank you, Renata. Can you hear me?
Yes.
Excellent. Thanks, Renata. So Renata just discussed and described the advent of ingredient diversification and increases in formulation chassis complexity. When you combine that with growing interest in leveraging technology to increase the speed of identifying viable solutions, those two things combined enable us to recognize the need and opportunity for developing technology that enables very rapid formulation, fabrication, and characterization across a broad range of formulation factor space. So with that in mind, we've developed a proprietary high-throughput system that prepares aqueous surfactant chassis formulations at extremely fast rates compared to manual bench formulation, on the order of 2 orders of magnitude faster production of formulation and data generation. The system's capable of working with a very wide range of surfactant chemistries that commonly reside in a formulator's toolbox. And in addition, each formulation is then rapidly characterized on the spot against targets such as viscosity and clarity to reveal trends, patterns, and ingredient interactions that would be difficult, time-consuming, and tedious, essentially impossible, to uncover via traditional methods using manual iterative formulation work. In addition to the wide range of surfactant ingredients that we can work with, we are also able to use fragrances and other additives, and we can readily investigate salt response, and we can easily vary ratios of different components and total levels of these components. By applying our capabilities using a highly structured design strategy for implementing the experiments, we are able to map formulation characteristics such as viscosity and clarity in such a way that we essentially fingerprint a formulation landscape. When we conduct such landscaping, for example, across alternative ingredients, various ratios, or in the presence of different additives, we are able to reveal trends, patterns, and ingredient interactions that would be difficult and time-consuming to uncover via the traditional methods. So one of the types of mapping procedures that we have found particularly useful generates what we call a binary heat map. So I'm going to walk you through how we read such a map and show you a couple of simple examples. In a binary heat map, we are varying 2 formulation factors at a time, captured in the X and Y axes, and representing a formulation characteristic such as low shear viscosity as a contour map. In the binary heat maps we're discussing today, the x-axis is weight fraction of a surfactant relative to another surfactant in the chassis. There can be other surfactants and other components in this chassis, but what we're varying is the ratio between 2 surfactants within the system, from 0 to 1. You can also think of those as essentially as ratios of those 2 surfactants. The y-axis is salt. It doesn't have to be salt. It could be pH, it could be percent actives. We've done all those types of mapping exercises as well, but the examples you'll see today, what's on the y-axis is salt. And then the contour, as you'll see in the examples, is represented by color. In most of our examples today, what we're showing is low shear viscosity. So let's look at a couple of example heat maps. In both of these maps, the weight fraction of the two surfactants in the formulation is being systematically varied from, so on the, for example, the left graph, you go from 0 to 1. When it's 0, it means for these two surfactants relative to each other, it's all anionic surfactant. And when the value is 1, it's all amphoteric surfactant, okay? Like I said, there could be other components in there, okay? For these maps, we are going from 0 to 8% salt, and you see that on the y-axis. And then the colors indicate the viscosity of the formulation. So blue means low viscosity, and different colors increasing towards red indicate the extent of viscosity build, going from essentially water thin up to 38,000 centipoise in the example on the left, so very high viscosity. For the map on the left, a combination of anionic and amphoteric surfactant, a rather broad range of surfactant ratios produces significant viscosity. In other words, it looks like an island, and this island is relatively large and broad. So you could be anywhere from practically no amphoteric up to about 0.7 weight fraction of amphoteric relative to the anionic and build a large amount of viscosity, provided enough salt has been added to the system. You can also think of, if you just start at 0% salt going to 8% salt, at any given sort of vertical line going across this map is essentially a salt curve for a given component fraction of the anionic versus amphoteric surfactant. However, if we change our surfactant chemistries, we see on the map on the right, the island becomes very thin. And occurs in a combination region that is shifted to about 0.8 weight fraction amphoteric. The thinness of this island, if you will, indicates that very high resolution mapping is needed in order to efficiently find this location of viscosity build. And it would be difficult to know that it's there without exhaustive mapping of the formulation space. Maps like these can be easily constructed for a wide range of combinations and can be generated for systems that contain any number of additional components, such as co-surfactants or, for example, fragrances. So with the capabilities I've just shown you, we're able to explore formulation factor space at a resolution that simply is not feasible via traditional manual bench work. Could you do it? Sure, in theory, you could do that. Each of those maps has literally hundreds of formulations and the associated data generation associated with them. So you could do it manually, but it's very unlikely that you would ever choose to spend those kinds of resources to do that, let alone how tedious it would be to generate data of that quantity. So with that, I'm going to hand you off to Cyril. He's going to guide you through an example of how he's been able to apply our mapping technology to very rapid prototype formulation solution identification that meets defined set of customer requirements. Off to you, Cyril.
Thanks, Greg. So kind of like what we were talking about before, let's apply what Greg has developed and provided to us in a real life application. Now, bringing back the slide that Renata talked about before, sulfate-free systems have a lot more components than what they used to have before, right? That means you're dealing with multiple primaries, multiple secondaries, right? It can be overwhelming. How many different components, variables, thickeners, and items that do we need to add into these formulations in order to get to our goal where sulfated systems just makes it a lot easier. What we have to do is we have to use tools, interactions, getting on the bench and just mixing it up, and then a system level thinking to really address those parameters and get to the same conclusion. You know, looking at this breakdown of a sulfate-free system, it's a lot of different surfactants and it can be paralyzing, right? I'm kind of curious to see what everyone else uses as their go-to sulfate-free formulation. So, Derek, if you can pull up our next poll question, excuse me. I wanted to know what surfactant chemistries are your go-to choice for sulfate-free systems? For shampoos, for cleansers, are they AOS? Are they any amino acid-based surfactants like torates or sarcosinates, APGs, alkyl polyglucosides, sulfosuccinates, or blends that can be primaries, secondaries, both of one, both of the other? I'm going to give you guys another minute to kind of start to vote and kind of show what's going out there. Going all the way through. This is actually very interesting, and I think you guys are going to like what we're going to be showing. A lot of you guys are talking about blends of primary and secondary surfactants. So I want you to keep that in mind for the next couple slides going through. But okay, we just got something from marketing, right? So we have a project that we're going to have to work through together, all of us, right? And you know how it is. We got to do it fast and we got to do it efficiently. Now, what marketing has brought us is a moisturizing body wash with the caveat that they want to be able to formulate it up, increase the solids, increase the actives to make a shampoo, and maybe formulate it down, right? Dilute it in order to make a hand soap at a later time. That's great. Thanks, guys. Some of the claims, kind of like what Renato was talking about. Sulfate-free, naturally derives, so my AOS is out the door. Salt-free thickening, always a very difficult situation and non-irritating. Characteristics, got to have a viscosity of around 5,000 to 9,000 centipoise, starting to become more common, easier to dispense from a bottle and pump, pH 5.5 to 6.5, and then that clarity. At least they're listening to us, right? Translucent to clear. We're not always going for the crystal clear, but at least we have that wiggle room. We're still going to shoot for the clear, though. You know how we work. Attributes, large bubbles, soft after feel, easy to rinse off, things we can work with. Absolutely. Now we're getting to the must-haves, right? 1% fragrance. We know that it kills our viscosity. It's going to be one of those hurdles that we're going to address as soon as we get to it, but that's usually where a lot of the problems arise. And it makes it more difficult because we have those non-polymeric thickeners. So, just thinking about all these different requirements and things inside of our portfolio to bring us to those targets. Using my experience with a lot of sulfate-free systems, we actually have a high efficiency surfactant blend, kind of like what everyone was voting on before, in Stepan Mild PCL-BA. That naturality complex, way better than AOS, right? If we look at the ISO 16128 score, it's 0.9, great. The preservative is benzoic acid, generally doesn't go against anyone's ingredient policy, so it's acceptable. Irritation potential on a scale of 1 to 100 is about 61. Actives, 25%, very easy to work with, right? I think I'm going to start to use it around 20%, maybe dilute it down as needed. I just really need to see where that performance threshold is going to be, and handling is going to be a clear liquid, right? So I know that it's easy to use at first, no problems. I can go. Next surfactant that I'm going to be adding with this one, or what I want to use, is going to be Cap B, right? Our Amphasol HCAHP. ISO 16128 score is going to be 64. There's no preservative, right? It's a high pH system. So it makes it a lot easier. I don't have to worry about incidentals. Irritation potential is 50, so a little bit lower than PCL-BA. Allows me to kind of modify whatever I needed from a formulation standpoint to hit whatever targets I need. Actives, 30%. Again, really easy to use once we have those concentrations. And then use level, right? I'm probably going to start around 15% and then vary it from there on an actives basis to kind of get my performance. And again, that's going to be a clear liquid. So I've started off with these two surfactants for my system to address what's needed in the project, right? Knowing about these surfactants, bringing this in from my experience, it's a great starting point. However, we're bringing in Greg's high throughput technology in order to help fast track formulation development. Now, let me show you what I used to do and how it can take a lot of time, right? Traditional approach, we're going to start with the stick in the mud, right? I'm going to start at a point, build some viscosity curves using salt and adjusting maybe pH, because there are multiple parameters that will adjust that. Maybe look at a couple DOEs to figure out what direction I need to go to after I see a response. And then I'll go through that again in an iterative fashion, modifying a couple variables to go through until I see or I understand what the characteristic is going to be like. Now, this can take weeks to months, and that can go from 12 batches to who knows, hundreds. It takes a lot of time. It's very frustrating at times, right? And because of the time constraints that we're all used to, that we have to deal with, we don't really have time to explore the formulation space and really understand those interactions. This is where learning is incremental, and the frequency is dependent on not only the batches, but the projects that are going through. A lot of times when we're going through a singular project, we don't understand what's going on until the end of the project. In turn, we have to get a lot of projects to gain even more insight, right? And that can lead to years of experience where, you know what, we don't have time to do that. With Greg's high throughput, what it does is it allows us to see surfactant ratios that are already prepared. The data is already organized in a binary map, just like what Greg was talking about before. You can get an exact ratio to start off with, as opposed to that stick in the mud. And then with a guided spot check, you can get to your conclusion, right? Hit those targets. These hundreds of data points that have been captured gives you a broad perspective of how to use these surfactants effectively and with greater precision, right? The formulation space has already been mapped, so you don't have to take those years of experience. You can start at ground zero and start to build from there, right? Set a new threshold for years of experience. The relationships of the variables, call down, right? We know what to do, now we just need to use it. And this allows us to become more informed and not assuming what's going to happen, right? All these are very empowering things taken from Greg's high throughput and applied to real life applications that we're showing you today. Now, let's take Greg's high throughput binary graph and use it in this practical application. Remember, we're using PCLBA and we're using HCAHP. We're trying to get all those different naturality complexes, performance things, and yeah, right here, we're going to start off with viscosity, aiming for that 5,000 to 9,000 centipoise. We can see kind of like what Greg was talking about. Looking at the heat map, there's a long island that we can see on the screen right now that gives us the optimal areas in order to get the highest viscosity, right? One thing you can also look at as you start to look at the y-axis on the left side is that it's very salt tolerant, right? So this also addresses one of the requirements and potential future projects where we might have to make a shampoo or a hand wash, right? Going through with salt is not necessarily going to break the system, could help it, right? Those are all things that we love to use because we always have our formulas that helps us fast track development. I'm feeling a lot better about this project. I'm seeing the results before I even go to the bench. But as we start to go through, remember, we can't use salt to thicken our system. So that's where I have to take my focus and look at the bottom part of the graph. 0% salt, we already have that island light up, right? So we have a broad area where we can actually formulate in order to get viscosity, which is great. And just kind of looking at it right now, I'm thinking that probably around that 0.6 weight fraction for Amphasol HCHP is going to be a great starting point for me before I even go to the bench. That 1% fragrance, it's always something that's going to pick at us as formulators, right? It could break the viscosity. I'm looking at this map. I've done it before. Someone says, hey, you're going to have great viscosity. And then I add the fragrance, it disappears, right? But let's try it. Let's take it to the bench. Let's see what we get. So I'm going to take that 0.6 weight fraction of HCA, and I'm going to translate it to my batch card in terms of actives percent to make it, and then see what the result I'm going to get. What this results in is going to be a 4.8% active of our Stepan mild PCLBA. Remember that high naturality blend that we were talking about before, and then 7.2% of the Amphasol HCAHP. Again, with no salt in there, 1% fragrance. Now, what do we get? Derek, I think you need to pull up that video just to show what the result of this is going to be. Oh my goodness. Oh my goodness. I'm so excited. Check this out. Check this out. It actually overshot the viscosity. Look at that gelatinous blob. Usually the viscosity breaks and it's water thin. We got something with 1% fragrance, no salt, and high viscosity, 60,000. That overshoots everything that we needed. It overshoots it, right? Because remember, as we started to develop the product and we saw the project requirements, we actually need to have a viscosity of around 5,000 to 9,000, right? We need to be able to have this product be pumpable. This is where I'm going to start to use my experience to dilute it, right? We're going to go through a couple iterations in order to decrease that total actives level to get a nice flowable product. Now, the end result, I got 3.0% active percent of the Stepan PCLBA, as well as a 4.5% of the Amstel HCAHP, all in actives percent. The total active percent went from 12 to 7.5% active in order to hit that viscosity target. Now, what did we get? Derek, let's roll that next footage. Here we go. Here we go. Are you watching? Look at how smooth that product is as we started to vary that actives concentration while keeping the ratios the same. We hit our target. We got 90,000 centiphores. This is exactly what we need. Now, before we go back to the slides, I need to tell you something, right? Looking at the graphs that Greg has provided in order to understand what the system is like, to go through the renditions, to make the batch, to adjust the batch, and to go through without knowing how these characteristics are. It took me about an hour. I'm a very skeptical person. I like to see the results. I like to experience the results at the same time, right? And it's saved me, just like it does for all you formulators. And I'm telling you, when I went through this, I was pleasantly surprised, excited to see that we can actually get real life applications in order to fast track formulation, understanding, and gain more insight. Let's go to the next slide real fast. Perfect. So now what we have is we've addressed, the current situation, body wash. We know that we can use this for other types of formulations, formulating up to a shampoo or down to a hand soap. We've hit all the claims: sulfate-free, naturally derived, salt-free, non-irritating. We've addressed the viscosity. We made it with 1% fragrance and we don't have any thickeners. That leads us to large bubbles and then clarity. Clarity is something that Greg also talked about in the previous slides as well when he started talking about high throughput. So as we look at this slide over here, you can see on the left side that his high throughput heat map now shows clarity as opposed to viscosity from what we saw before. Looking at the graph, you can see that the dark areas indicates that those are going to be the least or the smallest probability to get something that's going to be clear, where the light areas are going to be the highest probability of getting something clear. Remember, we picked the 0.6% or the 0.6 weight fraction HCA point, and you can see over there is very wide. If we started to go incrementally to the right, maybe 0.65, maybe 0.62, we were about to see a little bit less clarity, maybe translucent, maybe even opaque. But looking at both the viscosity and the clarity heat maps in the binary system, that's why we chose the 0.6. So we did a great job. We didn't even need to go through a bunch of renditions, right? So the high throughput has already allowed us to gain so much insight just to develop a product in less than an hour or around an hour. Now, the foam in the field. We know that PCLBA has quick flash foam with small bubbles, has a creamy foam feel, and it's non-drying to the skin. That's why we chose it, and you can see it on the screen right there. It's one of those things that, we still need to add that to the formulation layer, but, with Greg's high throughput, it makes it a lot faster. My anxiety has really subsided thanks to this high throughput. So just to kind of go over what marketing brought to us just on a whim and wanted us to develop really, really fast, like they always want, right? We're able to formulate something that's going to be very robust and versatile, right? Hit all the claims that they wanted. naturally derived, sulfate-free, salt-free, right? Thank you, salt-free. We hit the viscosity targets while maintaining the pH, and we have a clear product. We already have the large bubbles, the soft afterfeel, and the easy rinse off. And even with 1% fragrance, we did all of that with no polymeric thickeners, right? To go through these marketing briefs in this type of speed, accuracy, and precision, it really helps out. Now, if you're really interested in doing something like this, Renata has something to talk about that we can probably help you with. Renata?
Fantastic. Thanks, Cyril. That leads us to our final section, the partnership, how Stepan and us here within the personal care group can help turn that data into the decisions you all need for your specific formula. As Cyril said, he was skeptic, but you can see in this image, he believes we really make that sulfate-free formulating with this system so much easier, no matter what kind of different combinations, which can be so vast with that toolbox. And we can do that in a number of different ways. We just showed a few heat maps to give a good real life example, but we understand that your choices are going to be personalized. So we've got thousands of data points already mapped across these different combinations to help us guide and have that guided experimentation to get to your unique formula. Whether that's 2 components, 3 components, some of the different parameters like Greg was talking about, we've got that map. And we want to be able to partner with you and help you make that decision so much more easier when you're looking at formulating those sulfate-free formulas. Maybe you're looking for inspiration. You need something to start with. You want the full formula, not just a few combinations. No waiting required. We have so many formulas on our website around sulfate-free, depending on the types of claims or formats you're looking at. Just 2 examples related to today. We have a gentle cleansing body wash that has that moisturization, really popular within that claim space. And then also, if you're looking for something a little bit more experienced, a foaming body milk that gives that consumer something fun to play with and leaves smooth skin. Both of those are on our website and are just 2 examples of the hundreds that we have on the Stepan Formulation Finder. So check those out. Additionally, we've got a ton of helpful resources for building shampoos and cleansers. Maybe you want to start at the beginning. You want to better understand. You see a pop-up on the bottom left of your screen. If you click that button, you won't lose us. It'll open up a different window. You can check out all the resources that we've put together around guides, decision trees, and also claim data and how you associate these ingredients when you finally have a system to how you put claims on the front of the bottle. You can go to the resources page on that section and you'll have a vast list of different product guides and portfolio pages to explore. So feel free to click that. You won't lose us, I promise. And then finally, like we said, those formulas are unique. We need to differentiate and make different types of products on the market. If you want that hands-on support, we can connect you with a chemist, whether that's Cyril or someone else around the globe, for that personalized formulation building. You can reach out to your local sales representative or contact us at this page, go.stepan.com/sulfate-free webinar for an inquiry form, and we're happy to help you and come to that decision with all that data to make it easy and much more efficient. With that, this is the end of our content. We really want to thank you all for joining us today. I know we'll have time for questions. On behalf of myself, Cyril, and Greg, we know your time is valuable and really appreciate you spending, whether it's your morning or afternoon or evening with us. I'm going to hand it off to Derek to facilitate some question and answers.
Perfect. And as we get ready for this Q&A session, just as a reminder to the audience, you can submit your questions in the question box located in the bottom right-hand corner of your screen. We do already have a few that have already come in. Greg, this first one is for you. Shelf stability is an important factor in optimizing product formulation. Can you comment on your high throughput capabilities for stability?
Okay. You can hear me?
Yep, sure can.
Good. Great. Great question. Yeah, Cyril talked about clarity. He showed a clarity heat map. Just to clarify, no pun intended, clarity refers to initial clarity of formulation as it's being fabricated, right? So it's a measure of, let's call it instantaneous compatibility. It's a good indicator from the perspective of identifying things that are very likely to fail right out of the gate. If it comes out lacking clarity initially, it's unlikely to recover from that, although it's certainly possible that certain formulating procedures could help recover that clarity. So we use it as a screening tool. We do have capabilities for shelf stability measurement. We do not routinely practice it because it is quite labor intensive. It's a lot of materials handling. So we do that on a case by case basis. So when such situations arise, we're happy and able to support those situations, but we're not including that as a general screening tool at this point in time. So great question. Thank you.
And then Cyril, this next one here is for you. Does this mean that HCA-HP is the best choice for thickening all systems?
Not exactly, right? So when we start looking at these heat maps, we're identifying areas and combinations where HCA is going to be thickening very well, right? So it's providing insight for that, but the general rule is look at the heat maps before saying, yeah, it's going to thicken everything. It's more of it's going to thicken over here.
And then Greg, many formulations contain polymers in addition to surfactants. Are you able to include polymers in your high throughput formulating?
That's a great question. We didn't address polymers today, other than indicating that the formulations we showed were polymer free. We are beginning to work with polymer thickener systems in our capability. We do have a caveat today. Our capabilities are limited to liquid handling, so the addition of solid polymer powders and things like that is currently not in our high throughput wheelhouse. We are considering it for the future, but there's a fair amount of complexity in doing that. We are just starting to work with liquid-based polymer systems and exploring what the right methodology for incorporating those chemistries might be. Because again, when we develop these heat maps, this is not traditional DOE. It's a different sort of strategic experiment setup. So we have to both conform to the physical capabilities of our system, as well as take advantage, leverage, if you will, the efficiencies of our experiment design to do that mapping. So we're just getting started, is what I'm saying. And so hopefully we can come back at some point and share more about our progress on incorporating polymers. I'm bullish on it, but there will be some limitations.
And then Greg, do you have additional high throughput characterizations? And what other applications are you thinking about with this?
Okay, so there's two questions there. So I'll start with the first. Today, we have capabilities on viscosity measurement, clarity, and pH. We haven't talked about pH, but we have that capability as well. For viscosity, actually, we're able to measure at multiple shear rates. We can even customize a shear rate depending on how we configure our system. So we can get viscosity versus shear rate curves. In fact, we routinely generate those. We didn't share any data today, but that can easily be done. We can even automatically generate data fitting to those curves to provide insight in terms of how the formulation will respond to different flow rates and things like that. And this is relevant to line fill. It's relevant to behavior out of the bottle. It's relevant to how material spreads. So we're just getting started in exploring how to unlock the value in generating those large data sets. So that's where we've started. We are just now starting to work on additional characterization methods. And the first ones that we're focused on include wetting. So these are not necessarily geared towards personal care formulation work, because we are exploring other applications, which I'll describe. But we're looking at wetting, we're looking at dynamic surface tension, which is essentially a measure of how fast surfactants get to interface and reduce the interfacial tension. And we are working on towards the ability to do high throughput foam generation and characterization. This last one is a very, very challenging arena. And most of you may be aware that foam characterization is incredibly dependent on the method that's used, and one method doesn't necessarily translate to another. So we're excited to take on the challenge and see how far we can get with that. So with regard to applications, beyond the personal care rinse-off formulation space, we are working on other consumer applications, liquid dish, for example, and that's where that foaming capability would come in. We are also working towards supporting formulation technology in other markets, such as agricultural chemicals, such as oil field chemicals, and the like. So again, these are all works in progress, and perhaps we'll be back and talk about our progress on those as well in the future.
And Cyril, do these graphs provide other insights besides physical trends?
Yeah, so what we talk about is provided insights on, insolubilities of certain surfactants in different systems and how it actually affects the viscosity or other characteristics. So it's really interesting, we talked about how, before when you start to formulate, you just go, go, go. Using a high throughput and actually having the time to kind of look into these molecular interactions or incompatibilities or partial incompatibilities, it really helps for future developments and things that are here to come. So for right now, from what Greg was telling me, educating me, because I have to ask questions to him now that I have time, insolubility or partial solubility is really communicated and helps me understand what's happening in terms of viscosity and the other types of responses.
And then, Cyril, could you have used this HTP system to optimize fragrance? Why didn't you do that?
Yeah, so let's go with why didn't I do it? It was a fast project, and we all know about that, right? Get it done really fast. So we used the heat maps that we had on hand, right? Could we have used high throughput to raster through fragrances? Absolutely. And actually, I'm going to tag in Greg because he did talk about using fragrance inside of the high throughput system before, and he really explains it so eloquently. And I don't want to take that away from him. Greg, can you help me out?
Okay. Yeah, so we have started exploring in greater detail the impacts of fragrance on our heat maps. We can do it in any number of contexts. A couple things to be aware of. One is that if you're working with so-called water-soluble fragrances, those often will contain so-called solubilizers, which often are surfactant chemistries. They may have some solvent chemistry in there. Those chemistries can significantly affect viscosity. I'm sure many of you know that from your own experience by themselves without any of the fragrance oils actually added. And so we have begun mapping those effects. So we've started looking at specific solubilizer chemistries and how they might modify some of the heat maps that Renata shared out, for example. And in some cases, they turn certain areas on, and other cases, they turn other areas off. And so they change the level of the ocean, if you will. They change the mountain topography of the viscosity build and all of that. And so we're starting to build that understanding. We've also started working with individual fragrance oil components to understand how essentially the chemistry or the physical properties of the fragrance affects these maps in the same sort of way. So a non-polar fragrance component, for example, will generally tend to kill viscosity at certain levels, and we can actually quantify where they actually slightly boost and then they start to kill viscosity. We can do the same thing with polar oils, which generally tend to build viscosity or shift the salt curve to the left, things like that. And we're just starting to explore combinations. Now, in a commercial fragrance package, oftentimes you don't know the specific chemistries. So we understand that, and we're working towards a way of essentially characterizing, using the high throughput, characterize a given fragrance that is causing difficulties, in a standard way of mapping its impact, and then we believe we'll be successful in generalizing it across, say, the chemistry landscape by characterizing it in one way, should be able to get insight in how we expect it to behave across, a variety of chassis and conditions. So that's our goal. And I'll just add one last thing on this subject, is that if we're not working with so-called water-soluble fragrances, we're working with relatively water-insoluble fragrance oils. That does have some implications on how we do our experimentation. We've spent a fair amount of time working out the methodology to be able to accommodate those things. We do still have some, I would say, some constraints on that, but as we continue to develop our capabilities, again, I'm bullish that we're going to be able to make good progress on what is a very important problem, right? This is a well-recognized challenge in terms of predicting formulation. Is as soon as you add a fragrance or you change a fragrance, how's it going to respond, right? And so that's one of our primary focus areas right now, actually.
And then we did get a few questions about getting a copy of the presentation. Just so everybody knows, you will receive a link and a follow-up email that will give you a link to the recording of this webinar. So you will be able to review it after the webinar has concluded. The next question that we had here, marketing and tech-wise, does salt-free also include the salt that may come from the surfactants? This, I believe, is for Renata.
I'll take this one. It's a fun one coming from the technical space and then now being in the marketing side. With all things personal care claims, it's a nuance. Typically, and what is understood by the consumer is that salt-free is about no added sodium chloride to the system itself. We're not worried about the incumbent salt that might come in with surfactants, and will do. So as long as the back of that bottle can show that the sodium chloride isn't added, that is where we see the salt-free claim. Now, technically, right, we know that. So it's all about the positioning that you take. But in general, we're talking about the addition of the salt, exactly how Cyril was showing. We didn't incorporate more salt to the system to be able to thicken and to be able to be on the back of that bottle. So hopefully that answers that question.
I think we have time for one last question here, and this one is going to be for Cyril. What type of high-end space fragrance would you prefer to this? Would you prefer to the sulfate-free surfactant matrices? Often you could get haziness and low foaming or decreased viscosity.
That's a difficult one, and that's probably going to be something that we're going to be exploring a little bit more when we were talking about fragrances in the previous question. So I'm actually going to reserve the right to pause for that question. Let's talk about this offline, because we are going through this with high throughput, and we're probably going to have a little bit more developments, more than what we can really answer right now.
Perfect. Well, thank you again, everybody, for attending today's webinar. Just as a reminder, we will send you that link to the recording of today's webinars. You can watch it at any time and share it with others at your company. A representative of Stepan will follow back up with you guys in regards to your questions. Now, you will be redirected to Stepan's website for more information. Thank you again for attending, and we hope you have a wonderful day.